Welcome. My name is Oscar Rojas, Natural Resource Officer of the Food Agriculture Organization of the United Nations, FAO. We are going to talk about the Agricultural Stress Index System. This system was developed by FAO to monitoring the agricultural drought around the globe, and they was supporting the activities of GEOS, that is the Global Information and Early Warning System at FAO. The system was developed in collaboration with VITO, that is the Flemish Institute of Belgium for Remote Sensing, the University of Twente in Netherlands, and the Joint Research Center of the European Commission. When we start to develop the project, we were thinking that the possibility to use weather stations as access the drought in agriculture. However, the problem when we are using weather stations is that most of the stations are very sparse and provide discontinuous data. There's a lot of gap of information, mainly in Africa and other Latin American countries. The other possibility was to use rainfall estimate. However, to use estimation of rainfall, we need to have all the time error of this estimation, and in some areas we are going to find that the rainfall is over or underestimated. The last possibility was to use the vegetation index, and we decided to go with this, even if there are no perfect solution, because vegetation index can have noise when there are too more clouds or when the rainfall is too much, and then you are going to have saturation of the indicator. But at least it's no estimation, and when the sensor going to measure what is in the ground, is a direct measure that can be correct if there are some noise problems. Then the objective of the project was to monitoring agricultural drought in using geospatial information. And the system will be mimic the analysis that a remote sensing expert will do, and the final result will be expressed in maps that will be useful to interpret by any person that is no expert in remote sensing. The basic principle of remote sensing to monitoring drought in crops is the satellite going to capture different weights of length of the spectral radiation. They are not going to see the crops. We cannot distinguish where is maize or where is rice, but we can measure how is the reflection of the different bands. And we are going to use two bands, the red and near infrared. The red normally has to decrease during the time that the crop is developed. And then if they are not suffering from any, if the crops are healthy, what we are going to see in the registration of the satellites is a decrease on the red band and increase normally in near infrared. When they are water stress, the satellite going to capture more on the red, because in this case they are no use this red band for the photosynthesis production, because the stoma will be closed or partially closed. They will be reduced in the CO2 intake that is needed for the photosynthesis, and in this case we are going to expect to have a reduction of the crop yield. Of course, the reduction will depend if this water stress happen in the early stage that are less sensitive to water stress, or this same water stress happen during the sensitive technological phases like flowering or grain filling. We are going to use index that was developed by Kogan in the United States that is going to take two different variables. One is the biomass and the other is the temperature. In this case, we presented the vegetation condition index, and this is going to be a standardization of the NDVI. What we are going to take is the long-term minimum of the time series and the maximum of the time series. Between the minimum and the maximum going to be a standardization, then the data will be classified between 0 and 100. Close to 0, we are in front of a water stress of a drought in agriculture. In close to 100, the situation will be favorable for the development of the crops. The importance here is that we need a long time series. In this case, longer is the time series will be better because we can guarantee that each pixel going to have the historical memory of suffer for a string event. If you have short series like Modis or Spot, you can have, when you apply this kind of methodology based on the minimum and maximum, underestimation or overestimation of the drought events. In this case, we are using NOAA and METOP data that was intercalibrated to get a time series, unique time series of 30 years of information to guarantee that the pixel was suffered in the past of a string event of drought. Finally, the index will be the vegetation health index, that is the combination of the biomass by the vegetation condition index and the temporary condition index that will take in consideration when they are a drought. Normally the biomass will be reduced and the temperature will be increased. The final index, when you get low values, will be reflected in the ground as a crop failure, or when you have high values of the vegetation health index, we are expecting to have good crop conditions on the field. What is new and what is FAO introduced is in ASIS is integration in the temporal scale, that it will be, the indices will be integrated from the start of the season and to the end of the season. From the start to the end, each time that a new data every 10 days is going to arrive, will be integrated into temporal scale. What we are going to use is the administrative unit. In most cases will be the district level, that we are going to use acromas. That means that inside the district or municipal levels, we are going to take only the pixels inside of the agriculture area. Secondly, when we get the integration temporal, we are going to have a spatial integration. We are going to consider only the pixels that are affected by drought, and we are calculating the percentage of crop area affected by drought. That means the ASIS value will give you an indication in percentage of the area affected by drought. The chromas that we are using at global level is this one that summarize. We put together 10 crops, maize, sorghum, rice, that represent the cereal crops. And here in the bottom, we have chromas for the grassland areas at global level. We are using information from 1 kilometer resolution, and the system will be at global level update every 10 days. Here we show the start of the season, 1 kilometer for the first crop season, and the end of the season at global level for the first crop season. Here's the time scale. We know that different places of the globe, there will be start the season, in other places will be harvesting the season at the same time. The system at global level going to monitor 2 crop seasons. In the areas where bimodal distribution of the rainfall, we are going to have 2 crop seasons to assess. The system will be expressed the final results at district level. In the case of the United States, equivalent of district will be the county, and we here see that the information is much better to produce at this level to detect sensitivity areas, small areas that are affected by drought in the big department or province. The final results will be expressed in maps. In this case, we are showing the 1989, that we have a big drought around the globe. Curious, the 1989 was a La Nina year, and not El Nino year, that produced a lot of drought around the globe. The advantage of this ASIS system is that everything is integrated, and the users they need only to see the final map of ASIS. In this case, you can see here that this area was suffering for extreme drought. This area too. This area has in better condition, climatic condition to the production. There are no any noise of areas that don't have crops. Everything is masked out. In the classical analysis, it's more difficult interpretation because there are no detected where exactly are the agriculture areas. To analyze an anomaly of vegetation index, you need to see what happened before and what happened before to see how many of these anomalies are representing stress and how long this stress was affecting the different phenological phases. This is one advantage of the ASIS values, that you don't need only the final image in comparison with the classical analysis. In the case of Laos, you can see some indicator, the NDVA anomaly and bottom, and vegetation health index on the top for the different March of the different years, 2014, 15, and the most recent period, that is March, where you can detect some areas affected by drought in this area. However, you can find more information on the global website of FAO that we are going to show here. Every 10 days is automatically updated information. You can see here the different areas of the globe, and you can find, if you are looking for some specific country, information directly to here, or you can enter to the system directly in Agricultural Stress Index, and you get the global map where the crop areas affected around the globe. Here you can see now at the end of March where are the hotspots in this moment, that is Africa Austral. They are suffering for a drought very similar to what happened with El Nino 91-92. Morocco is affected by drought, and some areas in northeast of Brazil. If we want to go to a country level, it's possible to go directly from here, and we are going to look for Laos in this moment to see how is the situation in Laos. When we enter here, we can see when the blue is that the situation is out of season, and this month some areas started to planting. You can see here the progress of season, that they tell me how is the percentage of the evolution of the crop cycle. In this case, most of the indicator that is very early is only in planting stage in this moment at the end of March in Laos. Some areas already start to be a normal dry, but this can be a delay of the start of the rainy season. We have to see the progress. When you click on the map, you are going to see the legend and all the situations regarding to the whole country. We need to monitor closely these areas that already start with some kind of drought, but this can improve if the rainfall come after this. Other information that is possible to see is the vegetation indicator here, that you can see the anomalies of NDVA, the vegetation condition index that shows you how is the situation of the biomass production compared with the maximum and minimum, and vegetation health index that they integrate the VCI that I showed before with the TCI, that is the temperature effect. You can see month by month every time that you you need to see this kind of indicator, you can click and try to make some analysis. Also, you can see on the website the rainfall estimated by ECMWF, so the European Center of Medium Weather Forecast, and you can see the estimation of rainfall. You can see the anomaly of rainfall, that the situation seems to be very below normal. And you also go to the graph. You can compare the NDVA profile extract by province in this case, and you compare this year, the current year, with the previous year and the long-term average. You can see the precipitation. This is the average precipitation. This is the previous year, and in red is coming the current year, and this in light gray represent the maximum of rainfall, and here the minimum of rainfall. Remember that this precipitation is not calibrated, and calibration is important to see how good is the estimation of rainfall for Laos if they want to use this in operational way. We come back now again to the presentation. We can see now that the system was already tested with the previous drought in 94, that was the Sahel. You can see how is expressed by the index the big drought of the Sahel, some droughts in India, United States in the 80s, and this big drought in Africa Austral 91-92, that is very similar to what happened with the current El Niño phenomenon this year. And this is very interesting because I started working with FAO in 92 in Mozambique, and I was really surprised how drought was affecting the production of maize at that time. Other big droughts, 2003, happened in Europe, where there was a lot of people died, older people that was died by cardiovascular problems on this year, 2003, a big drought in 2006 in Australia, and more recently again droughts in Russia and Horn of Africa. We have based in the 30 years information that we have in FAO, we calculate the probability and to see some prone areas around the globe. And you can see this information in the publication that I am going to show after in the presentation. Based on this global project that was developed at FAO and now is operational on the website, you can have in the future, we are finalizing in May a new version that will be support countries and regions, and we call this standalone ASIS. The standalone ASIS is funded by the Global Improved Global Governance Hunger Production Project at FAO, funded by EU, and this will be implemented to link with the global data that will be installed in the countries, and the countries will be manage the system. The idea is that the standalone will connect to the global, going to cut the area of interest. For Laos will cut the whole country. In this case, going to download the archive, and every 10 days have to connect via FTP to download the new image. The data that can be downloaded will be TCA and BCE mainly, go into a database that can be hosted in a national institution. This is going to be calibrated with local information. The first calibration that we are going to do is to see how are, for the different crop, maize or rice, the sensibility of the two components of the vegetation health index. Based on the historical crop yield, we can see if PCI or TCI are more important to correlate with the crop yield. Then we are going to change in the global version, A and B have the equal value of 0.5, but in the case of national, we can change this value based in this correlation with the crop yield. Other important changes that will be provided by the standalone version is that we are going to weight it, the vegetation health index using crop coefficients. We know that the different phenological phases don't have the same sensitivity to water stress, and the most important phenological phases are the flowering and grain filling. Then the crop coefficient will be high, and the other part, like close to harvest or at the early stage, will be less sensitive, and we are going to use the crop coefficients multiplied by the index to show that if a drought happens during these sensitivities, will be give more weighting in the way that we are integrating the temporal indicator. Here's a 2 image that will show how when we multiply, the situation are different. In this case, our sensibility, we prove the sensibility. For example, this one that was this in green, this light green disappears when our weighting. That means that they are the stress happened during a very important phenological phases. Then we are modifying from the global our graphic. We are introduce the crop coefficient for the spatial integration. And other modification is that if you remember the first graph was only red and green, in this case we are going to have more categories of drought that was going to be defined by the user. The user now can define extra categories of drought. At the global level, we are working with only one category that is below, when vegetation health index is below 35, and we consider exceptional drought, but the user can define extreme drought, severe or moderate drought. For the studies, I can extract information the administrative unit that is working. The administrative unit can change in the standalone version, can be also agroecological zones if they want. Other possibility that's going to have the standalone version is to calculate probabilistic to forecast. We would like to know, we are in the middle of the crop season, how will be classified this pixel? That means that we can calculate the probability and the error associated to this probability. We are at the beginning of the crop season. That means that the probability will be close to the historical probability of the 30 years, the drought that happened in 30 years. But every time days that a new data arrives, every 10 days, we are going to adjust this probability, this historical probability, and we are going to get a dynamic probability, and we will be able to know what is the probability if you are in the middle of the crop season of the classification at the end, if the pixel will be classified as a not drop pixel or as a drop pixel, knowing the statistical error. This kind of probabilities can express in maps also the error of the interpretation of this probability. Here we test for the SIL. This is at the beginning, this is in the middle of the crop season that already forecast the drop pixels that will be more evident at the end of the crop season. Other application that is possible to use with the standalone version is to use remote sensing based in the crop assurance. The idea is to pass the climatic risk to the financial market. So we pass the climatic risk to the international markets of finance. In this case, we select Kenya as an example, province level, and we extract the ASIS value for the 30 years. If we want to sign a contract for crop assurance, we know that the trigger in this case will be 70% of the area affected at the eastern province. It will be triggered to cover 3 extreme events that happened in the past. If we want to cover more events, of course, the premium for the contract of assurance will be increased, and the premium will be different. For example, if we establish a contract in NASA that are less prone for drought, in this case the trigger will be 40% to cover only 2 extreme events of the past. Other possibility that we can use is that ASIS value can use in a model, a statistical model for crop yield forecasting. In this case, we forecast wheat and barley, and we see the R-squared explain 80% of the variation of the crop yield in Syria, and 74% in the case of barley for Syria. Then we can make an early estimation. The other possibility to use the ASIS value is inside to the mitigation plans of drought. We can use as a trigger. We have a ASIS value, and if this value is at the beginning is good, we are only planning, monitoring, and send some measures to the public to be prepared in case that we have a drought problem. If we are in a situation with the ASIS start to be low, we start with the monitoring, and we have to tracking more close the situation on the field of drought. And if we go down also, if the ASIS values start to be low, we go to the contingency plans. We have to save water, we have to move to drought-resistant crops. If the situation is very bad, then we go to the emergency response to save people on the field. The second part that I want to talk that you request me is about the El Niño impact, and we are going to use ASIS at global level to understand better how the El Niño influence at the global agriculture areas.